The goal in this video is to derive the closed-form solutions to the European call and put options using the Black-Scholes-Merton model. First, a couple of reminders. In the previous video, we discussed the Black-Scholes-Merton model for the stock price changes, which is also called the geometric Brownian motion. The main motivation here was to have the percentage changes, ds over s, as a constant drift and constant diffusion terms. So here, mu is the real-world drift of the stocks, and dw is a linear process, which is epsilon square root of dt, where epsilon is sampled from a standard normal distribution. Previously, we also discussed the Ito's lemma, which provides a stochastic derivative expression for any function g that depends on an Ito process S. Here, the Ito process is our Black-Scholes-Merton model with a is equal to mu s and b is equal to sigma s. Then we constructed a risk-free portfolio and argued that it should grow in risk-free rate r. And using Ito's lemma, we derived the Black-Scholes-Merton differential equation. Now, in this video, we want to find a solution to this equation. Specifically, we want to find a closed-form analytical solution to the European call and put options, which provide an option to buy and sell the stock at a strike price at the option maturity. One thing we noticed previously is that somehow the real-world drift mu in our model does not appear in the final differential equation. So this already gives us an idea that we might be able to play some tricks with the drift in the model. And indeed, we can do a so-called change of measure going from real-world drift to risk-neutral drift. So we're assuming that all assets grow at the risk-free rate r, and then later on we can discount by this factor again to find the present value. There are rigorous ways to show that this is allowed, but for now let's just take that as a given. Now let's consider the call option. The key idea is the following. The fair price C for this option is its payoff at the maturity, which is max of s minus k and 0, integrated by the appropriate probability density function, or PDF, at the maturity. We don't know the expression for this PDF yet, and it will be one of the main tasks for us to get the value of C. Then we can discount by the risk-free rate to get the present value. Next, we can simplify this integral by dropping max and changing the integral limits. Alright, so how does the FST look like? Well, we know that in the Black-Scholes-Merton model, the stock prices are log-normally distributed. Let's say the function g is ln s. Then dg can be obtained using Ito's lemma. We simply evaluate the needed partial derivatives and plug into the Ito's equation. This gives us a drift diffusion process, which is a generalized linear process, and this is known to be normally distributed. So if we integrate from the initial to the final time, we see that the log of st is normally distributed with this mean and variance. By the way, here we use the fact that variance of epsilon is equal to 1. Okay, so for if some variable x, we know that ln x is normal, what is the PDF of x? Well, we can use the relation from statistics between PDF and CDF, the cumulative distribution function. The PDF is just the derivative of CDF. So we plug in the definition of CDF, and then we can take the ln of these variables, because ln is a monotonic function. Then we standardize these variables by subtracting the mean and dividing by the standard deviation. Now we know that ln x is normal, so this is just the CDF of a standard normal distribution. Let's call that capital N. Next, we can apply the chain rule here. The derivative of CDF is the PDF multiplied by the derivative of the argument. And that gives us this expression. So we can take our ln_st distribution and plug in its values for mean and variance in the above expression. Note that this term is the mean of ln s over s0, so let's call this mu for simplicity. Okay, now that we have the PDF of the FST, let's come back to our integral. Plugging in the FST is going to give a pretty complicated integral, so we need to simplify it using a change of variable. Let's call ln s over s0 as x. Then we can substitute for s, ds, and the limiting value xk. Plugging in everything from the above, we see that there's some cancellation, and we get two integrals that we need to carry out. Let's call this one integral a and this one b and tackle them separately. Let's start with the part b, since it's the easier one. We see that this integral is just the tail probability of a normal PDF. To simplify this, we need to do another change of variable. Let's call z is equal to x minus mu divided by sigma times square root of t. Then this becomes a variable from a standard normal PDF. Then we can obtain x, dx, and xk to plug in the integral b. Putting everything together, the integral simplifies to 1 minus CDF, namely 1 minus nzk, but due to symmetry of standard normal PDF, this can be also written as n negative zk. So let's calculate negative zk. We will call this number d2 so that integral b is equal to CDF of standard normal at d2. Now let's move on to the part a. Here we have this additional e to the x, which complicates the integral. The trick here is to multiply and divide this by another exponential as such. Then, if we write out the two exponents in the integrand, we see that we can get a term which is a complete square. Now we can do a change of variable yet again. Let z be this expression, and from here we can substitute for x and dx. Putting everything together, the integral a can be written as such. After some simplifications, we again get an integral of standard normal PDF. Here we use the expression for mu to simplify the exponential. Again, we can evaluate the value of negative zk and call that d1. This gives us the integral a as e to the rt multiplied by CDF at d1. Now we just put integral a and b together. This gives us the final closed form solution for the European call option. Next, for the put option, we can go through a similar set of integral calculations. But it's much easier to use the call-put parity once we have the value for the call. So plugging in C, we get the value for P as well. Once again, D1 and D2 limits are given as follows. By the way, you might have noticed that these final expressions look like the payoff formulas, and indeed, we can interpret them similarly. Here, ND2 is the probability that the call will be exercised in a risk-neutral world. And the first term here is the present value of the expected stock price at maturity when S is counted as 0 for S smaller than K. Finally, why should we care about the analytical solutions for the European options? After all, what we really care about is the American options, as they are traded more frequently in practice. Well, when we calculate the values of American options, the European options provide us a good sanity check. They give us a lower bound, as we know that American options should be equal or higher in value than European options because they have the extra flexibility to exercise sooner. Also, if we are calculating American options numerically, the exact solutions to the European options provide us a control variate. So for example, when using binomial trees, the control variate can reduce the bias due to the coarse mesh of the time. It also helps if we're simulating it using Monte Carlo by reducing the sample variance. Finally, the analytical solutions for the European options also helps us with the pricing of exotic options.